Above ground, the Australian outback can look almost unfinished. The light is hard, the soil is exposed, the grasses stand in dry clumps, and distance seems to flatten everything into emptiness. Heat presses down on the plain until the air above the ground trembles. A wedge-tailed eagle can cross the sky without casting more than a passing shadow. A dingo can move through the scrub and disappear without leaving anything obvious behind except a shallow print in dust. To an untrained eye, this landscape looks open, simple, and brutally honest. But that is the mistake. The most important architecture here is not above the surface at all. It is beneath the feet, cut into clay, sand, gravel, and compacted earth by one of Australia's most underestimated engineers, the Wombat. A wombat does not look like the builder of a hidden city. It is low, heavy, broad-backed, and almost comically blunt, as if evolution took a grazing animal and compressed it into a living shovel. But that body is not clumsy design. It is excavation machinery wrapped in fur. The shoulders are powerful, the forelimbs are short and muscular, and the claws are built for tearing into soil with a persistence that few animals in this environment can match. Even the pouch, turned backward instead of opening toward the front, is part of the engineering story, keeping loose soil from being pushed inside while the animal digs. The wombat is not simply hiding underground. It is physically shaped by the act of creating underground space. The entrance to a wombat burrow can look modest from a distance. A dark oval cut into a slope, a mound of loose soil pushed outward, a worn track leading away through the grass. But that entrance is only the doorway. Inside, the tunnel may bend and descend, widening in places where the animal turns, rests, or escapes the worst conditions above. In some systems, multiple openings connect through deeper passageways, turning a single burrow into something closer to a subterranean network than a simple den. The deeper sections hold their own atmosphere. While the surface swings between daytime heat and night cold, the burrow slows those extremes down. Temperature becomes less violent, humidity becomes more stable. The wombat has built what the open landscape refuses to provide, a controlled microclimate. This matters because the outback does not kill only with teeth, it kills with exposure. A summer day can turn bare soil into a heat plate. Shade may be scattered, unreliable, or already occupied by other animals. Waterholes shrink. Wind carries dust. A mammal forced to remain above ground through the hottest hours must spend water and energy just to keep its body from overheating. The wombat solves that problem by withdrawing into architecture. During the day, it can remain below, reducing heat stress and conserving moisture. At night, when the air cools and the risk of overheating drops, it emerges to graze. The rhythm is simple on the surface, but biologically it is a quiet negotiation with climate. Feed when the world allows it, disappear when the world becomes expensive. The burrow also changes predator pressure. A wombat outside its tunnel is not helpless, but it is not built for long-distance escape. It cannot outrun the open country the way a kangaroo can. Its defense is strength, position, and terrain. When threatened, it can retreat into the burrow and turn its reinforced rear toward the entrance, using its body like a plug in the tunnel. That hard, compact backside is not glamorous, but it is brutally practical. A predator that follows a wombat underground is no longer attacking a soft animal in open space. It is pushing its face into a narrow passage against a muscular wall. The chase becomes a geometry problem, and the wombat designed the geometry. But the deeper truth is that wombat burrows are not useful only to wombats. Once the tunnel exists, the land around it changes for other animals too. Small mammals, reptiles, birds, and invertebrates may use the entrance zone or deeper sections as shelter, shade, humidity refuge, or temporary safety. This is where the wombat becomes more than a resident. It becomes an ecosystem engineer. By moving soil, breaking compacted ground, and opening cavities beneath the surface, it creates habitat that other species could not easily build for themselves. The Outback's secret city is not organized like a human city, and the wombat is not intentionally running a public shelter. That would be a cute myth, and cute myths are usually where science goes to die. The real story is better. One animal's survival structure becomes part of the survival equipment of the whole landscape. During fire, that role becomes even more dramatic. When flames move across dry grass and leaf litter, the surface is transformed in minutes. Heat rises, oxygen shifts, smoke thickens, and animals that cannot fly or flee fast enough are forced into any refuge that exists. Wombat burrows do not magically save everything, and wombats are not standing at the entrance politely directing traffic like emergency workers. But the tunnels are real, and their value is real. Underground space can remain cooler and more protected than the burning surface. After fire, when cover has been stripped away and food is scarce, the entrances and surrounding disturbed soil can become important recovery points. Animals moving through a blackened landscape may find shade, shelter, and sometimes moisture around these structures. The burrow becomes a memory of the landscape before the fire, a pocket where the world did not burn in the same way. Drought sharpens the same pattern. When water disappears from the surface, survival becomes a matter of reducing loss as much as finding gain. A cool burrow helps conserve body water. The soil around burrow systems may collect runoff differently, hold moisture in pockets, or create small differences in vegetation around the entrance. These effects can look minor if measured one at a time, but in a harsh environment, minor differences are often the difference between movement and collapse. A lizard that avoids the worst heat for an hour has bought time. A small mammal that finds cover near a burrow entrance has reduced its risk of being seen. A bird foraging near disturbed soil may find insects exposed by the digging. The wombat's construction work ripples outward through the food web, not as charity, but as consequence. Even the soil itself is changed. Digging brings buried material upward and pushes surface material down. It mixes layers that would otherwise remain separate. It loosens hard ground, opens small pathways for air and water, and creates mounds where seeds can lodge and germinate under slightly different conditions. Over long periods, this matters. Ecosystems are not only built by rain and plants and predators, they are built by bodies moving earth. Termites do it with towers. Ants do it with galleries. Burrowing reptiles, rabbits, bilbies, and wombats all reshape ground in different ways. The wombat's version is heavy, muscular, and long-lasting. It does not just pass through the country, it edits the country. There is also a timescale hidden in these tunnels. A grazing animal above ground may seem temporary, appearing at dusk and vanishing before the heat returns. But a burrow can persist. Entrances may be reused, expanded, abandoned, reopened, or inherited by new animals over time. The landscape keeps the signature of the wombat even when the wombat itself is out of sight. This makes the animal easy to underestimate. A kangaroo announces itself with movement. A crocodile announces itself with threat. A venomous snake announces itself, sometimes too late, with consequence. The wombat announces itself with infrastructure. Its power is not in sudden violence. Its power is in making a landscape more survivable by cutting shelter into it. That is why the wombat is the strongest opening for this underground story. It takes the false emptiness of the outback and breaks it open. The surface may look quiet, but underneath it is organized by tunnels, chambers, airflow, temperature gradients, scent trails, worn entrances, and dark passageways that become important when the surface turns hostile. Heat, fire, drought, and predators all define life here, but the wombat answers them with excavation. It does not migrate away from the harshness, it digs into it. And in doing so, it creates one of Australia's most important hidden systems. Not a city of lights or noise, but a city of cool air, packed earth, survival routes, and refuge zones beneath a landscape that only looks empty because most of its engineering is underground. Scientific anchors checked. Recent research describes wombat burrows as ecological hotspots and post-fire refugees for other species, while burrow microclimates can reduce heat and water stress in harsh. The echidna enters the outback without hurry, and that is exactly why people underestimate it. Against a dry slope of grass, stone and fallen bark, it looks like a moving burr, a small armored mound pushing through the landscape with its nose lowered to the earth. It does not have the obvious authority of a wombat, no great tunnel entrance behind it, no permanent underground hall system that can be pointed to and called a home. It seems temporary, almost accidental, as if it has wandered into the scene from a stranger branch of evolution and forgotten to explain itself. But watch the ground behind it. That is where the story appears. The echidna is not building a city beneath the outback. It is doing something more restless and more widespread. It is opening the surface again and again, cutting small doors into a world most animals only walk across. Its body is a strange collection of tools, and none of them are decorative. The short legs keep it close to the ground, where scent, vibration, and soil texture matter more than speed. The long snout works ahead of the body like a probe, testing cracks, litter, roots, termite galleries, and ant trails. Its claws are not the claws of a predator built to seize prey in a chase. They are the claws of an animal built to break sealed things open. A crusted patch of soil, a rotting log, a buried insect nest, a surface baked tight by heat and dryness. All of these are barriers to most animals. To the echidna, they are invitations. It lowers itself, braces through the shoulders, and begins to dig with the stubborn rhythm of a machine that does not care whether the ground was supposed to stay closed. This is where the echidna becomes part animal, part excavation device. Its food is hidden, and hidden food demands a different intelligence from open grazing or pursuit hunting. Ants and termites live behind walls, inside mounds, under stones, beneath bark, in narrow chambers where chemical trails organize thousands of tiny bodies into working systems. The echidna hunts these societies by entering their architecture from the outside. It tears into the nest with its claws, pushes its snout into the breach, and flicks a long, sticky tongue through the exposed galleries. Insects that were moments ago moving through sealed darkness are suddenly dragged into daylight, attached to a tongue that moves too quickly for their defenses to solve. The echidna is not fast across the landscape, but in the exact zone where speed matters, the feeding strike inside a broken nest. It is brutally efficient. Every feeding pit it leaves behind is small compared with a wombat burrow, but the scale is deceptive. Echidna digging is not impressive because of one giant structure. It is impressive because of repetition. A wombat changes a place by committing to it. An echidna changes a landscape by touching many places lightly but constantly. Across woodland, heath, grassland, and arid country, its foraging creates pits, furrows, loosened patches, exposed roots, disturbed litter, and broken soil crusts. Each mark may look minor in isolation, but together they form a quiet pattern of bioturbation, the living reworking of Earth. Soil that would otherwise seal over under sun and wind is opened. Leaf litter that would remain on the surface is pulled into hollows. Seeds are trapped where moisture can reach them. Organic matter is buried where microbes can break it down more effectively. The echidna is not planting a garden with intention, but the ground does not care about intention. The effect is real. In dry Australian landscapes, this matters more than it would in a softer, wetter world. A hard soil crust can shed water too quickly, letting rain run away across the surface before it sinks down where roots and microbes can use it. A shallow echidna pit interrupts that movement. It catches leaves, sand, seeds, insect fragments, and moisture, turning a tiny scar in the ground into a small collection point. After rain, these depressions can become miniature resource traps, holding the ingredients for plant growth in one place long enough for life to take advantage. In a landscape where fertility is often patchy and thin, the echidna creates little islands of possibility. The irony is almost rude. An animal searching for ants accidentally helps the plants. The opening of the soil also exposes hidden life to other hunters. When an echidna breaks into a nest or turns over litter, it does not consume everything it disturbs. Small invertebrates scatter. Beetles, larvae, termites, ants, and other soil animals are forced into motion. Birds may later inspect the disturbed patch. Reptiles may search the warmer, exposed soil. Predatory insects may find wounded prey or disrupted trails. The echidna's feeding does not end with the echidna. It briefly changes access to an underground community, and in doing so, it changes who can feed there. The ground is not an inert floor. It is a layered habitat, and the echidna repeatedly punches holes through the roof. That hidden world theme is built into its senses. The echidna does not need a dramatic face or forward-staring predator eyes because it is not reading the world like a cat. It is reading close-range information from the ground. Its snout, stiff and sensitive, searches through smell, touch, and subtle signals around buried prey. The animal's attention is downward, investigative, almost geological. It pauses over a patch of dirt that looks empty, then begins to work as if it has found a locked compartment. For viewers, that is the visual power of the echidna. It reveals that the outback surface is lying. What looks like plain ground may contain tunnels, eggs, larvae, colonies, moisture pockets, roots, fungal threads, and entire food chains moving beneath the dust. Its defense completes the same idea. When threatened, the echidna does not perform like a classic prey animal. It does not sprint into the distance. It does not leap, bluff, or depend on panic. It turns the ground itself into armor. If cover is close, it may push into it. If the soil allows, it digs downward with startling force, sinking its body until the soft underside is protected and the attacker is left with a dome of spines locked into earth. The claws grip into roots, pebbles, and compacted soil. The body lowers, the spines flare outward, and the animal becomes less like prey and more like a geological problem. A fox, dog, goanna, or curious predator can nose at it, paw at it, and circle it, but the echidna has changed the terms of the encounter. It has stopped being a moving target and become part of the ground. There is something almost absurd in that defense, but it is not weak. It is beautifully practical. The echidna's underside is vulnerable, but the back is armored with sharp keratin spines. By digging down or curling tightly, it presents the part of the body least worth biting. A predator looking for flesh meets a pincushion anchored to Australia. This is not courage, it is design. The echidna survives because it knows, in the language of muscle and instinct, that the surface is not just a place to walk. It is a shield, a pantry, a refuge, and a door. Heat adds another layer to this relationship with the ground. Echidnas are mammals, but unusual ones, and their physiology does not fit the standard image of a high-speed, high-temperature animal constantly burning energy in the sun. They often avoid extreme heat by seeking shelter in logs, vegetation, crevices, or soil. Their slower pace is not laziness, it is energy economics. In harsh country, survival does not always belong to the animal that moves fastest. Sometimes it belongs to the animal that spends least, overheats least, and knows how to disappear when the surface becomes dangerous. The echidna's digging is part of that broader strategy. It is not only feeding behavior. It is a way of negotiating climate, predators, and exposure with the same toolset. This is why the echidna belongs immediately after the wombat. The wombat shows the outback as a place with hidden infrastructure. The echidna shows how that hidden world is constantly being opened, sampled, stirred, and renewed. It is not a city builder, and forcing it into that role would be trash biology. Its real power is different. The echidna is the living drill, the surface breaker, the animal that turns sealed ground into active ground. It walks across a landscape that appears dry and quiet, then leaves behind evidence that the earth is alive beneath the crust. A nose presses down, claws start cutting. Soil loosens, ants scatter. Seeds fall into pits, moisture gathers. Predators investigate, microbes begin their invisible work. And the echidna moves on, carrying its little armored body toward the next closed patch of earth. Above ground, the outback still looks empty to anyone moving too fast to read it. But the echidna reads it slowly, with its snout, claws, shoulders, and appetite. It reveals that beneath every dry surface is another layer, a food layer, a shelter layer, a memory of rain, a buried architecture of insects and roots. It does not simply live on the surface. It tests it, breaks it, enters it, and leaves it changed. In a world where survival often depends on finding what is hidden, the echidna's genius is brutally simple. When the ground refuses to open, it makes the ground open. Scientific anchors. The Australian Museum describes short-beaked echidnas as ant and termite feeders that use their pointed snout and claws to break into nests, while UNSW research explains how echidna digging creates pits and depressions that trap litter, seeds, nutrients, and moisture, improving soil function over time. The first warning is usually too small to respect: a round opening in the soil, a cleared patch of gravel, a few large ants moving with strange confidence across the dry surface. They do not look like a swarm at first. They do not pour over the ground in black rivers like army ants, and they do not advertise the size of the hidden system beneath them. That is what makes them dangerous. Above ground, the scene looks manageable. One ant near a stick, another crossing a bare patch of dirt, a third standing near the entrance with its jaws open and its body angled upward. But the mistake is thinking the visible ants are the whole animal. With bull ants, the real organism is not the worker you can see. The real organism is the buried colony below your foot. A bull ant nest is not just a hole, it is a defensive installation built into the soil. Beneath the entrance, the ground opens into shafts, chambers, brood areas, worker traffic routes, and protected spaces where larvae develop away from sunlight, drying wind, and surface predators. The entrance may be small or partly hidden, but the nest can extend deep enough to turn a patch of ordinary ground into a vertical fortress. Soil, small stones, plant fragments, and cleared material around the opening can reveal the colony's presence, but only if the viewer knows what they are looking at. To everyone else, it is just rough ground. That is the scary part. The outback does not need to look threatening to be occupied. The colony below is organized around survival. Workers move through dark galleries where temperature and humidity are more stable than on the exposed surface. Larvae wait in protected chambers, completely dependent on the adults that feed, clean, move, and defend them. The queen is not a battlefield commander in the human sense. She is the reproductive center of the colony, the living source from which future workers and males can emerge. Around her, the nest functions as a biological machine. Food comes in, waste and debris move out. Young are protected, damaged entrances are repaired, and any serious disturbance near the surface is treated as a threat to the entire system. This is why the underground army angle works. Bull ants are not army ants in the strict biological sense, and pretending they hunt like one huge coordinated swarm would be trash science. Their rebellion is different. It is not constant mass invasion. It is territorial defense from a hidden base. Above ground, bull ants often appear as individuals, and those individuals are unnervingly capable. Many ants rely heavily on chemical trails and group movement, but bull ants are famous for their large eyes, strong vision, and direct awareness of intruders. A worker can look less like a blind particle in a swarm and more like a small animal making decisions. It turns, it tracks, it faces movement. It can move quickly toward disturbance with jaws open and sting ready. That visual alertness changes the emotional tone of the scene. The ant is not simply wandering, it appears to be watching the border. Near the nest, that border matters. A footstep scraping soil, a stick pushed into the mound, or vibration passing through the entrance area can change the colony's behavior in seconds. The visible worker becomes an alarm point. More workers appear. The nest entrance, which looked like a harmless opening a moment ago, becomes a release valve for aggression. Ants emerge from below and move toward the source of disturbance, not because they are angry in a human way, but because natural selection has made nest defense brutally valuable. The brood underground cannot run. The queen cannot abandon the colony every time a large animal approaches. The colony survives by turning the entrance into a weaponized threshold. This is what gives bull ants their rebellion feeling. Wombats build refuge. Echidnas open the ground. Bull ants militarize it. Their nest is hidden infrastructure with a surface defense system attached. The soil becomes a bunker roof. The entrance becomes a guarded gate. The workers become sensors and soldiers operating between two worlds, the dark colony below and the dangerous surface above. For an insect that may be only a few centimeters long, this is an extraordinary use of space. The bull ant does not need to dominate the landscape physically. It only needs to control the small zone around the nest with enough force that larger animals learn to avoid it. The sting is the final argument. Bull ants have mandibles for gripping and a sting capable of delivering venom that can cause intense pain and, in some people, serious allergic reactions. The mandibles are not just decorative jaws. They help anchor the ant to the target so the sting can be driven in. This combination of grip and venom makes a worker more than a nuisance. It becomes a compact defensive unit, able to make a much larger animal retreat from a tiny patch of earth. A kangaroo may pass by. A bird may investigate and think better of it. A reptile searching for insects may turn away if the surface starts moving. Even humans, supposedly the dominant species in the scene, become clumsy giants, learning the oldest rule of nest defense. Size matters less when pain is delivered with precision. The colony's underground life also changes the surrounding ecology in quieter ways. Workers bring prey back to feed larvae, often targeting other insects and small arthropods. They collect sweet secretions and interact with plant and insect resources above ground. Around the nest entrance, the soil is disturbed and sorted. Stones, fragments, and debris may be moved. The cleared area can alter how sunlight reaches the ground and how water moves across the surface during brief rain. These changes are smaller than wombat excavation and less widespread than echidna foraging pits, but they still matter because they show the same deeper theme. Australian ground is not passive. It is constantly being occupied, defended, opened, sealed, and modified by animals that most viewers would step over without thinking. Inside the nest, the colony depends on division of labor, but not in a way that needs to be exaggerated into fantasy. There are workers that forage, workers that tend brood, workers that maintain the nest, and individuals positioned near the entrance where outside danger first appears. The colony's intelligence is distributed through many bodies, each responding to chemical cues, movement, contact, light, scent, and disturbance. No single worker understands the whole fortress, but the colony behaves as if the fortress must survive. That is the power of social insects. They do not need individual imagination to produce collective strategy. The strategy is built into repeated behavior. For the viewer, the camera should stay low here, almost at ground level, where the nest entrance becomes enormous. The dry grains of soil look like boulders. The ants move through shadow and sunlight, their bodies glossy, their jaws open, their legs gripping the uneven ground. Behind them, the outback stretches quiet and bright, but the important world is not the horizon. It is the black opening below the ants. That hole is the whole chapter. It says the surface is only the lid. Underneath, there is traffic, brood, heat balance, stored labor, and a colony ready to answer intrusion with violence. This is also why bull ants belong in the middle of the underground rebellion. They shift the video from shelter and soil disturbance into defense. The hidden world is no longer only protective or ecological, it is territorial. The ground has boundaries. The entrance has consequences. A person walking through dry scrub may believe they are crossing empty land, but from the colony's perspective, that giant foot is crossing the roof of a nursery, a food storage route, a queen's chamber, and the future workforce of the nest. The ants do not need to understand any of that as a concept. They only need to respond. The strongest image is not 1,000 ants spread across the frame. That would weaken the truth. The stronger image is a few workers visible at the entrance, while the narration makes the viewer feel the unseen pressure below them. Because that is how bull ants work on the imagination. You see a few. You are standing over many. You think it is a patch of soil. It is a buried fortress. And once the surface defense system activates, the outback stops feeling empty. It feels occupied from underneath. Scientific anchors. Australian Museum describes bull ant nests as usually underground. often with small or hidden entrances, sometimes extending several meters below ground, and notes their aggressive defense and strong vision. CSIRO similarly describes bull ants as aggressive, visually capable ants that can rapidly emerge from nests when disturbed. Museums. Victoria notes that most species nest underground in soil, sand, rocks, debris, decaying stumps or logs, and that workers catch insects to feed their larvae. For most of the year, the forest floor gives almost nothing away. Leaves rot quietly under the trees. Bark strips curl away from trunks. Ants move through the litter. Skinks pause in patches of sun. And the soil seems to belong mostly to roots, fungi, and whatever has already died there. It is easy to think of this surface as the bottom of the world, the place where everything falls and decomposes. But beneath it, hidden in the dark, another generation is waiting. Not sleeping in the simple sense, not dead, not paused, but living slowly, feeding quietly, growing in secret. The cicadas' rebellion begins long before the sound of summer. It begins underground, where thousands of wingless nymphs are attached to plant roots, drawing fluid from the hidden plumbing of the forest and measuring their lives in years instead of days. A cicada is usually remembered by its adult form, the dry shell clinging to bark, the clear wings, the sudden explosive song that seems too loud to come from an insect. That is the public version, the brief surface performance, but it is not the main life. The main life happens beneath the soil, where the young cicada lives as a nymph after hatching from eggs laid in plant tissue. Once the young nymph drops to the ground, it burrows down and enters a world without sunlight. There, it uses specialized mouthparts to feed on plant fluids from roots, especially xylem sap, the thin, watery transport system that carries minerals through plants. It is not a rich meal. Xylem is dilute, so the cicada must build its body on patience, persistence, and a strange economy of survival. It becomes a creature of slow extraction, taking just enough from the root network to grow through hidden stages while the world above forgets it exists. This is why cicadas fit the underground rebellion better than almost any animal in the sequence. Wombats carve shelter, echidnas break the soil open. Bull ants defend a buried fortress. Cicadas represent something different, time stored underground. They are not violent engineers or armed guards. They are a buried population, spread beneath the trees, attached to the living foundation of the ecosystem. The ground is full of them before anyone hears a single note. Every quiet summer before emergence is misleading because silence does not mean absence. It means the colony of future sound is still below the surface, feeding. The nymph's body is built for this hidden world. It is squat, wingless, and equipped with strong digging forelegs that allow it to move through soil and maintain contact with roots. It does not resemble the delicate flying adult that will later cling to a trunk and split its own back open during the final molt. Underground, elegance is useless. The nymph needs grip, pressure, and a body that can live surrounded by particles. It has to survive compacted ground, shifting moisture, root growth, microbial decay, and the constant possibility of being found by predators that specialize in the soil. Beetle larvae, ants, spiders, centipedes, and burrowing vertebrates all move through this lower world. To live underground for years is not to live safely. It is to live inside a crowded, dark economy where danger is close range and often unseen until contact is made. The feeding itself links the cicada to the forest in a quiet but intimate way. A tree may appear still above ground, but below its roots are drawing water, exchanging nutrients with fungi and pushing through cracks in search of stability and supply. The cicada nymph taps into that system. It is not chewing leaves in the canopy or stripping bark in a visible attack. It is drinking from the root layer, hidden so completely that the adult tree may show no obvious sign of its small passenger. This relationship is parasitic in the broad sense, but usually not dramatic in the way people imagine animal attacks. It is low intensity, distributed, and long-term. The nymph survives by staying modest. It does not need to kill the plant. It needs the plant to continue pumping. Years pass this way. Rains come and go. Fire seasons tighten the air. Grass grows, dries, collapses, and returns. Trees flower, birds nest and leave. Reptiles shed skins under logs. Mammals cross the same patch of ground without any awareness that beneath them, a cicada generation is slowly assembling itself. This is the hidden scale that makes emergence so powerful. The adult event looks sudden only because the preparation has been invisible. A viewer sees the forest floor open in one night and imagines an invasion. In reality, it is the end of a long underground childhood. The cues that draw cicadas upward can involve soil temperature, moisture, rainfall, and seasonal timing, depending on species and location. This is important because the story should not be reduced to one simple timer. Australian cicadas are diverse and their life cycles vary. Some species may spend several years underground. Some large common species can show multi-year patterns, while other species are less neatly understood. That uncertainty is not a weakness in the story, it makes it stronger. The underground world is not a mechanical clock with one setting. It is a living system responding to climate, plant condition, soil moisture, and developmental readiness. When the right window arrives, the sleepers begin to move. Then the rebellion becomes visible. At first, it may be only a small hole in the soil, round and clean enough to look deliberate. Then another. Then dozens. At dusk, when heat softens and shadows climb the trunks, nymphs begin emerging from beneath the leaf litter. They pull themselves upward with strong forelegs, slow and heavy, each one carrying years of underground growth inside a body that has never flown. The forest floor, which seemed sealed, begins releasing insects as if the earth itself has decided to exhale. They climb grass stems, saplings, fence posts, bark ridges, anything vertical enough to lift them away from the ground. For a creature that has lived in darkness, this ascent is both migration and transformation. The nymph is leaving the world that made it and entering the world where it must reproduce quickly before its brief adult life runs out. The molt is one of the great biological images of Australian summer. The nymph grips bark with its claws and becomes still. Along the back, the old skin splits. A pale adult pushes out slowly, soft, vulnerable, almost ghost-like. Wings unfold not as ready-made tools, but as crumpled membranes that must expand, harden, and clear. The adult waits exposed, while its body changes from underground machinery into airborne sound. This is the dangerous interval. Birds, spiders, ants, lizards, and mammals can take advantage of newly emerged cicadas before their bodies harden. Many do. Emergence feeds the ecosystem. A mass rising from the ground is not only a reproductive event, it is a sudden food pulse for predators, a seasonal offering that turns years of root fluid feeding into protein above the surface. That predator pressure helps explain the advantage of emerging in numbers. When many cicadas rise together, predators can eat heavily and still fail to consume them all. This is not bravery, It is mathematics. A single cicada climbing a trunk is an easy meal. Thousands emerging across a landscape can overwhelm the capacity of birds, reptiles, ants, and mammals to take every individual. The rebellion is synchronized, not because cicadas are marching with intention, but because timing can turn vulnerability into survival. If enough bodies appear at once, some will make it through the night, harden their wings, climb higher, and begin the adult phase. And then the sound begins. The male cicada's call is not casual noise. It is reproductive machinery made audible. Specialized structures called tymbals buckle in and out rapidly, producing pulses that can build into the intense chorus associated with hot weather. In large numbers, the sound can dominate the entire landscape, transforming the forest from a quiet underground nursery into an acoustic arena. The same insects that spent years hidden in soil now advertise from trunks and branches with almost reckless volume. It feels like a contradiction, but it is really the second half of the same strategy. Underground life is concealment and growth. Adult life is exposure and urgency. The cicada spends years being almost invisible, so it can afford a few weeks of being impossible to ignore. This is the chapter's strange beauty. The cicada's rebellion is not a battle, not a fortress defense, not a predator attack. It is a rising. The ground opens, and what comes out is not an army with jaws or venom, but a generation that has been living below the audience the entire time. It changes how the forest floor feels. Every patch of soil becomes suspect. Every root system becomes a hidden feeding site. Every empty evening becomes a possible threshold before emergence. The outback and woodland surface stop looking like a flat stage and start looking like a lid over time. By placing cicadas here, the video widens the meaning of underground survival. The wombat showed architecture. The echidna showed excavation. The BullAnt showed defense. The cicada shows patience on a scale that is almost alien. It survives by withdrawing from sight, feeding slowly, waiting through seasons, and emerging when timing gives the greatest chance that enough of its kind will escape predation and reproduce. Above ground, humans hear the final chorus and call it summer. Beneath that sound is a darker truth. The forest has been storing voices underground for years. Scientific anchors. Australian Museum states that cicadas spend most of their lives as underground nymphs and feed on plant sap, while CSIRO describes the life cycle in which hatched nymphs drop to the ground, burrow to roots, feed on sap for several years, then climb to the surface and molt into winged adults. Reporting from cicada researchers in Australia also notes that emergence can be shaped by temperature and rainfall cues, and that life cycles vary by species rather than following one universal timetable. The Perentie changes the mood of the underground world because it does not use the earth only to hide from danger. It uses it to become dangerous again. In the open heat of the Australian interior, where the light can bleach stone and turn exposed ground into a punishment, this giant monitor lizard moves through the landscape like a predator built from patience, muscle, and calculation. It is not a burrow engineer in the wombat sense, and it is not constantly opening the soil like an echidna. Its relationship with underground space is colder than that. A burrow is a retreat, a temperature chamber, a nest site, a hunting base, and a reset point. For the Perentie, disappearing below ground is not surrender, it is strategy. At first, the animal can seem too large to belong to the hidden world. A full-grown Perentie carries the presence of something ancient: long neck, powerful limbs, heavy claws, a muscular tail, and a forked tongue that flicks through the air like a chemical instrument. Its body is low to the earth but never weak. Every movement suggests stored acceleration. It walks with deliberate control, pausing often, tasting the air, lifting the head, reading the terrain through scent and movement rather than wasting energy on useless wandering. In a cooler forest, a predator might simply keep moving until it finds prey. In the Australian interior, movement itself has a cost. Heat is not background. Heat is an opponent. That is why the burrow matters. A reptile does not generate body heat the way a mammal does. Its performance depends heavily on the temperature of the environment around it. Too cold, and the muscles slow. Too hot, and the body approaches danger. A Perentie must manage this thermal window with precision. In the morning, it may bask, raising body temperature until its muscles and nerves are ready for serious movement. But by the middle of the day, the same sun that powered the predator can begin to threaten it. The surface becomes too exposed, too dry, too expensive. Then the Perentie can vanish into shade, rock crevices or burrows, dropping out of the killing light and into a more stable underground climate. This is not just comfort, it is survival physics. In hot desert environments, below-ground retreats buffer animals from extremes that would be brutal or impossible to endure on the surface. Air underground changes more slowly, soil insulates, humidity can remain higher. The burrow becomes a thermal refuge where a reptile can stop losing water, reduce exposure, and keep its body from crossing dangerous limits. For a predator, that refuge is more than a shelter. It is a place to protect the machine. Muscles, digestion, sensory processing, sprint capacity, and endurance all depend on the body not being cooked by its own landscape. The Perentie's strength begins with knowing when not to be seen. A burrow also breaks the rhythm of pursuit. The open country favors visibility, but it also exposes every animal inside it. Prey animals watch shadows, smell air currents, listen for movement through dry grass, and use open distance as an alarm system. A large monitor crossing bare ground is powerful, but it is also readable. Underground space allows the Perentie to remove itself from that surface conversation. It can disappear into a hole at the base of a rocky outcrop, under hard clay, or near a shelter used repeatedly over time. The landscape seems to go quiet. Birds resume feeding. Small reptiles return to sunlit stones. A mammal may cross the edge of the burrow system without understanding that the predator has not left the scene. It has simply moved into the part of the scene that prey cannot easily read. This is the predator's reset. After hunting, overheating, feeding, or being disturbed, the Perentie can retreat, cool down, and wait until the conditions improve. It can reappear when the light changes, when shadows stretch, when prey becomes active again, or when the surface temperature shifts back into a usable range. That timing matters because predation is not only about strength, it is about arriving when the other animal is vulnerable and the predator is ready. The burrow gives the Perentie a way to control its own readiness. It can leave the fight, repair its thermal balance, then return with the body restored. The claws tell the same story. They are not delicate tools. They are built for gripping rock, climbing when necessary, tearing into soil, and opening access to prey or shelter. Perenties can dig, use burrows, and may also take advantage of shelters made by other animals. That flexibility is important. A predator does not need to build every piece of terrain it uses. It needs to recognize useful terrain and occupy it. A burrow made for shelter can become a hunting position. A hollow that protects against heat can become a hidden base near prey movement. A tunnel entrance can become a place where scent collects, where tracks pass, where smaller animals hesitate, and where the predator's body can remain out of sight until movement is worth the cost. This makes burrows strategic territory rather than simple hiding places. The area around a retreat can shape the Perentie's daily route. It may include basking stones, escape cracks, feeding zones, nest sites, and pathways used by other animals. A good shelter is valuable because it is connected to the rest of the animal's life. It is not just a hole in the ground, it is part of a hunting map. From that map, the Perentie can move between heat, shade, prey, and safety. The outback may look open, but for a reptile, it is divided into usable and unusable temperature zones. A bare patch in full sun may be lethal at 1 hour and useful at another. A shaded crevice may be a refuge at noon and a cold trap at night. The burrow sits inside this changing grid like a control room. Nesting adds an even deeper connection between predator and underground space. Like other monitor lizards, perenties reproduce by laying eggs, and those eggs require protection and stable conditions during development. Soft soil, deep sandy areas, and termite mounds can provide more controlled environments than exposed ground. For a large reptile, choosing where to place eggs is not a small detail. It determines temperature, moisture, predator access, and the odds that hatchlings will emerge into a survivable world. The underground is not only where the adult survives the day, it is where the next generation can begin, sealed away from the harshest surface conditions before it ever sees sunlight. The prey side of the story is just as important. Perenties are carnivorous opportunists, taking reptiles, birds, eggs, mammals, arthropods, and carrion when available. That diet makes them part hunter, part scavenger, and part excavator of opportunity. A burrowed animal, an egg chamber, a nest beneath sand, a carcass hidden in shade, or a small reptile retreating into cracks all become possible targets in a landscape where food is never evenly distributed. The Perentie's forked tongue samples scent molecules and feeds information to the Jacobson's organ, helping locate direction and source. This is not random roaming, it is chemical tracking across a hot, broken map. When the Perentie emerges, the scene can turn fast. A still entrance becomes motion. A head appears first, then the shoulders, then the long body sliding into sunlight. The tongue flicks. The limbs lift the body into a more active posture. The predator that was absent seconds ago is suddenly present, warmed enough to move, cooled enough to continue, and close enough to matter. A small mammal freezing under scrub, a lizard exposed between stones, a bird nest placed too low, or an egg chamber scented beneath the surface may all fall inside its search pattern. The burrow has not made the Perentie passive, it has made it punctual. This is why the Perentie belongs late in the video. It changes the underground theme from refuge into weaponry. The wombat builds survival infrastructure. The echidna opens the hidden soil layer. The BullAnt defends a buried fortress. The cicada rises from years of secret life. But the Perentie shows the darker truth. Underground space can help predators control when the conflict happens. It lets them vanish from the surface economy, manage the body, wait out hostile heat, and re-enter the landscape at an advantage. Defense and offense are not separate categories here. In the outback, the same hole that saves an animal from heat can also make it a better hunter. The strongest image is a dry, rocky slope at noon, empty except for heat shimmer and the thin sound of insects. Nothing seems to be happening. Then, from the shadow under a stone ledge, the Perentia's tongue appears, tasting the air before the rest of the animal follows. The predator has been there all along, held beneath the surface while the world above burned through its worst hour. Now the temperature has shifted, the ground has become usable again, the fight has been reset. Scientific Anchors, the Australian Museum, notes that perenties shelter in burrows and shade to escape daytime heat, have strong limbs for digging and climbing, and are carnivorous opportunists feeding on reptiles, birds, and eggs. Desert animals in general often survive heat by using underground shelter. Research on Australian desert reptiles shows that burrow systems can strongly buffer temperature and humidity extremes, which explains why below-ground retreats are so valuable in hot environments. Additional Perentie references describe extensive burrows with multiple entrances or exits, use of other animals' burrows, and nesting in sandy soil or termite mounds.